In the grand cosmic ocean, there are countless worlds, each with its own story. But some stand out. They call to us across the vast distances of space, whispering of possibilities we've only dreamed of. One such world is Titan, the largest moon of the ringed planet, Saturn. It is a place of profound mystery and scientific wonder. What makes Titan so special? It is the only moon in our entire solar system known to possess a thick, substantial atmosphere. This isn't some wispy exosphere. It's a dense blanket of gas, even more substantial than the air we breathe right here on Earth. This simple fact sets Titan apart as a truly unique celestial body. Imagine floating down through Titan's sky. You would be enveloped in a perpetual, hazy twilight. The light from the distant sun struggles to pierce the thick, orange-colored smog that cloaks the entire moon. This atmospheric shroud is made mostly of nitrogen, just like Earth's. But it's the other key ingredient, methane, that drives the world's most fascinating processes. High above the surface, sunlight and cosmic rays bombard these methane molecules. This cosmic energy breaks them apart and allows them to recombine into a rich soup of complex organic compounds. These compounds, known as tholins, drift down like a constant, gentle rain, painting the entire world in shades of orange and brown. This thick atmosphere creates a pressure on the surface that is about 1.5 times that of Earth's at sea level. If you could stand on Titan without a spacesuit to protect you from the cold, you wouldn't need a pressure suit. You could walk around, feeling a familiar push against your body from the air. This Earth-like quality is tantalizing. It makes us think of our own planet's distant past. Some scientists believe that Titan's atmosphere today might be a frozen snapshot of what Earth's atmosphere was like billions of years ago, before life began to pump oxygen into our skies. It is a planetary time capsule. What this thick, hazy blanket hides is just as extraordinary as the sky itself. For centuries, astronomers could only guess what lay beneath Titan's orange clouds. We could measure its size and its orbit, but the surface was completely obscured, a secret locked away from our telescopes. It wasn't until we sent a robotic emissary, a machine built of curiosity and ingenuity, that we finally pulled back the veil. The Cassini-Huygens mission gave us our first glimpse of this hidden realm. It revealed a world that was strangely familiar, yet profoundly alien. A world of mountains, valleys, and rivers, but sculpted by forces and materials unlike anything on Earth. Let's descend through the orange clouds and explore the surface of Titan. The first thing you would notice is the cold. It is a deep, penetrating cold, with temperatures hovering around a staggering minus 180 degrees Celsius, or 90 Kelvin. At this temperature, water is as hard as granite. Water ice forms the very bedrock of this world, creating mountains and crusts that are frozen solid. But Titan is not just a static, frozen ball of ice. It is the only other place in the solar system, besides our Earth, where we have found stable bodies of liquid on the surface. These are not oceans of water, but vast lakes and seas of liquid methane and ethane. This discovery, made by the Cassini spacecraft, was a revelation. We saw dark, smooth patches concentrated near the moon's poles, which reflected radar signals in just the way a liquid surface would. We have named them Kraken Mare, Ligeia Mare, Punga Mare. These are vast seas, larger than some of Earth's Great Lakes. Flowing into them are river channels, carved into the icy terrain over eons. Just like Earth has a water cycle, Titan has a methane cycle. Methane evaporates from the lakes, forms clouds in the nitrogen sky, and then falls back down as rain. This liquid methane rain erodes the landscape, creating a dynamic and ever-changing world. Beyond the polar seas, the landscape of Titan continues to surprise us. Stretching across the equatorial regions are vast fields of massive dunes. These are not dunes of silicate sand, like we find in the Sahara Desert. Instead, they are made of dark hydrocarbon grains, the complex organic materials that constantly rain down from the atmosphere. These particles are sculpted by winds that blow across the surface, piling them into long parallel ridges that can be hundreds of miles long and hundreds of feet high. It tells us that Titan has weather, with winds that are active and powerful enough to shape the very face of the moon. And there may be even more dramatic features. Scientists have spotted formations that look suspiciously like volcanoes. But on Titan, these wouldn't be volcanoes spewing molten rock. They would be cryovolcanoes, or ice volcanoes. Instead of hot lava, they would erupt a cold, slushy mixture of water, ammonia, and methane from deep within the moon's interior. This activity could be a vital link between the surface and what lies beneath. Deep below the miles-thick crust of rock-hard water ice, evidence strongly suggests there is a massive hidden ocean of liquid water. This subsurface ocean could be a place where the chemistry for life might just exist. Titan is more than just a geological curiosity. It is a giant natural laboratory for exploring the origins of life itself. The conditions there, with its dense, nitrogen-rich atmosphere and abundance of complex carbon molecules, are thought to be very similar to the conditions on a very young Earth, long before life emerged. This makes Titan a priceless destination for astrobiology. We can study the chemical processes happening there right now to understand the steps that might have led from simple, non-living matter to the first living organisms on our own planet. It's like having a time machine to witness the dawn of creation. The chemistry of Titan is endlessly fascinating and continues to defy our expectations. For instance, the atmosphere is rich in hydrogen cyanide, or HCN. On Earth, this molecule is a poison, but for prebiotic chemistry, it is a crucial building block for amino acids, the components of proteins. A recent discovery in 2025, based on laboratory experiments and simulations, showed something remarkable. At Titan's frigid temperatures, polar molecules like hydrogen cyanide can actually form stable structures called co-crystals with nonpolar molecules like methane. This breaks a fundamental rule we learn in chemistry class, that like dissolves like, and opens up a whole new world of possible chemical interactions on Titan's surface. Another exciting theoretical discovery, published in mid-2025, explores what might happen when methane rain falls into the hydrocarbon lakes. Scientists at NASA proposed that the splashing action could cause certain organic molecules to spontaneously arrange themselves into tiny, hollow spheres called vesicles. These structures are essentially microscopic bubbles, with a membrane separating an inside from an outside. On Earth, all life is made of cells, which are basically vesicles containing the machinery of life. Finding that these cell-like structures could form naturally in Titan's methane lakes suggests that the first steps toward life might not even require liquid water. This rich organic soup on the surface and in the atmosphere is constantly interacting with the energy from the Sun and Saturn's magnetic field. This creates an ever more complex array of molecules, a kind of chemical playground where the building blocks of life are being formed, mixed, and altered. While the extreme cold on the surface probably prevents life as we know it from taking hold, these materials could be transported downward. They could seep through cracks in the icy crust, eventually reaching the vast liquid water ocean that we believe is hidden deep below. There, in that dark, warmer environment, the story could be very different. Our journey to understand Titan began in earnest with the Cassini-Huygens mission, a joint venture between NASA and the European Space Agency. For 13 years, from 2004 to 2017, the Cassini orbiter flew past Titan more than 100 times, using its powerful instruments to peer through the haze. Its radar mapped the surface, revealing the lakes, rivers, and dunes for the first time. It analyzed the composition of the atmosphere, confirming the presence of complex hydrocarbons. The mission was a resounding success, transforming Titan from a mysterious orange ball into a complex and active world. It gave us a foundation of knowledge, but it also gave us a whole new set of questions. The most dramatic moment of the mission came on January 14th, 2005. The Huygens probe, which had traveled with Cassini, detached and plunged into Titan's atmosphere. It descended for over 2 hours, taking pictures and measuring the environment around it. It then landed on the surface, becoming the first and only spacecraft to ever land on a world in the outer solar system. For a precious 72 minutes, it sent back data and images from the ground. We saw a floodplain covered with rounded pebbles, likely made of water ice that had been smoothed by flowing liquid methane. For the first time, we were not just observing Titan, we were there. But Cassini and Huygens were just the beginning. To truly understand the potential for life on Titan, we need to go back and explore its surface in detail. That is the goal of NASA's next ambitious mission, Dragonfly. Scheduled to launch in 2028 and arrive at Titan in the mid-2030s, Dragonfly is unlike any mission before it. It's a nuclear-powered, dual quadcopter, a flying rotorcraft the size of a small car. It will be able to fly from one location to another, exploring diverse environments across tens or even hundreds of miles. It is a drone built for another world. Dragonfly's mission is to search for the building blocks of life. It will land in a region where we know complex organic materials are abundant, and where there might be evidence of past liquid water. Its instruments will drill into the surface to sample and analyze the composition of the materials, looking for the chemical signatures of prebiotic processes. It will study the atmosphere, the surface, and the shallow subsurface to understand the habitability of this alien world. By flying to multiple sites, Dragonfly will give us a regional perspective on Titan's chemistry, helping us piece together the story of how a world so different from our own could hold clues to one of the universe's greatest questions. Are we alone?